consider you have x-axis and y-axis. Okay, so you have some curve. So let's say y is equal to f of x is the curve. Now, what if I have to find the area under this particular curve? So when we say under the curve, we need to have boundaries, correct? So initial point and the final point, we need to have boundaries. So let's say x1 is the initial boundary and x2 is the final boundary, meaning we are trying to find the area of the curve between these 2 points. Okay, so as you can look at the figure, this will be the area, correct? So now a very basic thing, if you have to find the area of a big room, so one way of doing that would be find the area of one tile and count the number of tiles in the room. If you multiply it, you will get the total area, correct? So we are going to do the same logic here also, but in place of one square tile, what we do is we use a rectangular area. Okay, so rectangular areas, multiple rectangular areas we'll consider. So area of this rectangle plus this plus this plus this. So the whole thing, if you add, that's nothing but the area under the curve, right? Now one more thing what you guys have to know is how big the rectangle should be, because when I say rectangle, it could be the whole thing or it could be very minute also, correct? Now if you think logically, lesser the width of the rectangle, more accurate will be the area, correct? So if you increase the width of the rectangle, there will be some sort of area which will be missing or which will be adding to it, correct? So it won't be accurate. For accuracy purpose, the width of the rectangle should be very small, so small that it should almost be zero. Like it's not zero, it's almost zero, correct? So we'll call that value as, let's say, dx. Okay, now every point if you see on the graph, that's nothing but y value, correct? Because y is equal to f of x, right? So if you take x1 as the initial point, then f of x1 will give you the value of y, that is nothing but this point. Then same thing, if you take x2, then f of x2 will be this point, right? So what we have is the points on the curve is nothing but the value of y, correct? So the length of the rectangle, what you are choosing, that's nothing but f of x, which is nothing but y value, correct? So the area of the rectangle is what? L into b. So in this case, it's nothing but y into dx. In other words, f of x into dx, right? Now every area of the rectangle you are adding, right? Addition is nothing but summation, correct? So sigma, if you can use here sigma, but remember one point, sigma is for discrete values, not for continuous values. Okay, so sigma is for discrete values, not for continuous values. So since these are all continuous rectangles, we use integral. So integrate meaning what? To sum up things, right? So integration of y dx. Now from which point to which point are we choosing here? From x1 to x2. So integral of y dx from x1 to x2. x1 is the lower limit, x2 is the upper limit. So this will give you the whole area under the curve. So the area will become a is equal to integral of f of x dx from x1 to x2. Okay, now why this much of information is needed? Because what you will be learning now is whatever the variable force you have, okay, the variable force is acting on an object, what is the work done by that? Okay, so remember the first derivation what you did was for a constant force, right? Now what you are doing is for a variable force. Now the work done is nothing but the area under the curve. Okay, so it's the area under the curve. So what we have is, see, this is the particular graph. Okay, you have different forces, meaning this is a variable force. Now from one point to one point, this is from x1 to x2, you're trying to calculate the work done by that variable force. Okay, that's nothing but the area under the curve. All right, So since we are talking about area under the curve, what we do is we take small values. Okay, so we'll call that as delta x here. So what we have is work done will be f of x into delta x. So now I'm assuming you guys already know what is f of x because just now we did it. F of x is nothing but the length of the rectangle, right? So in this case, it's the value of the force at that particular interval of time, a very small time. Okay, so f of x into delta x. Now, since we have to add up everything, we have sigma x1 to x2 f of x into delta x. Okay, now delta x has to be very small, right? Remember, lesser and lesser the value, more and more will be the accuracy. So we take limit as delta x tends to 0, sigma x1 to x2 f of x into delta x. So this will convert to integral of x1 to x2 f of x dx. So the area under the curve, the whole curve, this is the work done by a variable force. Understood? So let me just repeat the whole thing. What you have is you have variable force and you're trying to calculate the work done. So for this, you split the whole area into small rectangles of delta x as the breadth and f of x as the length. You calculate the area of each and every rectangle, you sum them up, that will be the total work done. Okay, so the work done W is equal to integral of x1 to x2 f of x dx. So this is the total work done.